Please make sure you have your copy of the assignment Strengths of Acids and Bases, Part 2. What we're going to do in this experiment is we're going to compare the strength of two acids, acetic acid, which is the acid in vinegar, and hydrochloric acid, which is an acid you can find in your stomach. Now let's just review what acids are all about. Acids are molecules that dissociate. That means they come apart into two pieces. One is a hydrogen ion, or a proton, and the other we call the conjugate base. We call it the conjugate base because it's the pair to the proton, and that these two things can join back together again and form the acid. A base is something that reacts with hydrogen ions and forms the conjugate acid for that base. So the reaction really goes in both ways. We're going to focus on the direction of dissociation. Now, when you look at the amount of acid that you have in a solution, we can measure how much it dissociates by measuring the hydrogen ion concentration in the solution using a pH meter. What we're going to try to find out in this experiment is how much of the dissociation reaction actually occurs. For every one acid molecule in this balanced reaction equation, if it dissociates, I should make one proton. If I had two of these, then I would make two protons, and so on. The amount of the acid and the amount of the hydrogen ion that dissociates from the acid should be equal if 100% of the acid dissociates. If all of this is used up to make all of these, then however many units of the acid I started with, I should end with the same number of units of each the hydrogen ion and the conjugate base. So what we'll try to find out is if 100% of dissociation occurs for each of these two acids. The more an acid dissociates, the stronger it is, and the less it dissociates, the weaker it is. So we'll compare the concentration of acids before and after they are diluted to make the solutions less concentrated, and then we'll measure the pH to see does the amount of hydrogen ion that we get compare equally to how much we started with. So, take a look on the front. There are some procedures. I'm going to do a demonstration today for the hydrochloric acid, and then tomorrow you can do the acetic acid in lab. I'm going to follow these steps, and then I'm going to record data for hydrochloric acid on this data table on the back, and then I'll show you how to do the calculations for hydrochloric acid and how to plot the results. And then when you do the lab yourself, you'll have an example to use so that you can complete the work independently. The procedures are going to take you through the steps in preparing a series of dilutions, starting with a concentrated mixture of acid. I'm going to demonstrate with hydrochloric acid. Its concentration is 1 mole per liter. And then we're going to reduce the concentration in a series of steps, each time dividing the concentration by 10. So we'll end up with a much less concentrated solution at the end. So what you'll need to do is start by using a graduated cylinder to put 90 milliliters of water into each of 4 cups labeled 1, 2, 3, and 4. And then take the acid solution, our starting solution, and a pipette. The pipette is marked where to stop measuring for exactly 10 milliliter volume. And put 10 milliliters into the first cup. And when we do that, it's going to add up to 100 milliliters. There's already 90 in there. So this 10 makes 100. And so 10 of those 100 milliliters is the acid that I started with. That means I've chopped the concentration by a factor of 10. So what I'm doing right now is I'm trying to mix a solution by drawing it in and out of the pipette. I can also swirl like this. It's important to make sure that it's really well mixed before you go to the next step. So let me draw that in and out one more time. Now the next step is I'm going to take 10 milliliters of this solution and put it in the next cup so I can divide its concentration by a factor of 10. So let me draw that up to the line, the stop line, 10 milliliters, and then to the next cup. So now this should be 100 times less concentrated than what I started with because I divided the first step by 10, and then I divided that 10 by 10, so now I'm up to 100-fold dilution. Let me draw that in and out of the pipette a couple times just to make sure it's really well mixed. The better mix this is, the more your results are going to make sense. Alright, then I'll go to the next one. I'll draw 10 milliliters up and go to the next cup. So that's why we call this a serial dilution, because it's done in series, one after the other. Okay, swirl that around and mix. And after these are all prepared, then what I'll do is I'll put them on the pH meter to measure their hydrogen ion concentration and compare that to what we would expect it to be if the acid was 100% dissociated. If it was 100% dissociated, then the hydrogen ion concentration should be the same as the acid concentration, because all of the acid molecules that are in the mixture will have dissociated to make hydrogen ions and the conjugate base. So here's the last one. And draw that in and out a few times, make sure it's really well mixed. Okay, and swirl to mix. Okay, let's get the pH meter out and see what we've got. For cup number 4, we'll record the pH 4.09. For cup number 3, we'll record pH 3.07. For cup number 2, we'll record pH 2.05, 2.04. Let's go with 2.04. For cup number 1, we'll record 1.02. And for the bottle, we'll record 0.02, 0.01. Let's go with 0.01. Okay, here are the results of our experiment so far. When I tested the pH of each of the dilute acid solutions, the bottle came up with a pH of 0.01. That's a very, very low pH. That means that there's a lot of acid. And as we decrease the amount of the concentration of the acid in each of the cups by a factor of 10, the pH increases, it looks like by a factor of almost 1, because there's less and less acid. The less acid there is, the higher the pH, the more acid there is, the lower the pH. So in cup number 1, a pH of 1.02, cup number 2, 2.04, cup number 3, 3.07, and cup number 4, 4.09. Now what we want to do with these pH values is figure out what's the hydrogen ion concentration so that we can compare it to what it says it should be. If the concentration is supposed to be 0.10 moles per liter, then let's find out if that's what we actually got. Did the acid dissociate 100%? So down below, we'll do calculations to find out what's the observed hydrogen ion concentration given the pH value using the calculations that we practiced last week. And then we'll calculate the percent of the acid that actually dissociated. So, starting with the first one right here, if the pH was 0.01 and I want to find the hydrogen ion concentration, then I'll use the calculation 10 raised to the negative pH. So I'll use my second function key, 10 to the x, and the negative pH, 0.01. And it says that the hydrogen ion concentration is 0.98 moles per liter. And then the next one, the pH was 1.02. So here I'll do the same calculation. I'll say 10 to the negative 1.02. And that will be 0.095 moles per liter. And then the next one, the pH was 2.04. So using our calculation, I'll say 10 raised to the negative 2.04. And that comes out to 0.0091 moles per liter. And then 3.07 for cup number 3. So here I'll find out 10 raised to the negative 3.07. Getting more zeros here. 0.00085 moles per liter. And then the last one, pH of 4.09. So here I'll say, try that again. 10 raised to the negative 4.09. And that is a lot of zeros, 0.00081 moles per liter. What we want to know is, of the acid that was put into the solution, how much of it dissociated? What percentage dissociated? If the solution was 1 molar and all of the acid dissociated, then it would make a solution of 1 mole per liter of hydrogen ions. And evidently we don't have quite 1 mole per liter of hydrogen ions. We got pretty close. So to find out what the actual percentage was, we'll take the observed hydrogen ion concentration, this one here, and divide it by what we expected, that one there, times 100 to make it a percent. So you'll see the pattern as soon as we do this a few times. You won't even have to use the calculator. 0.98 divided by 1.0 times 100 equals 98%. No surprise there. The next one, 0.095 divided by 0.10 times 100 equals 95%. See the pattern? Can you predict what this one's going to be? That one's going to be 91%. And this one will be 85%. And that one will be 81%. It's interesting that the percentages are going down. I wonder if there's less acid in those solutions because I made an error in my dilution. Maybe my measurements weren't good. But what we see is that there's a pretty high percentage of acid that is dissociating in each one of these mixtures. And one way that we can represent that is by putting it on a graph. So what we'll do with our data here is on the chart that's on the next page, for each of the different concentrations, what was the dissociation? So for example, the first one right over here, our pH of 1.0 was 98% dissociated. So up here I'll put a point for 98%. For the 0.1 solution, it was 95% dissociated. So I'll put a point right there. For the 0.01, it was 91% dissociated. And for the 0.001, it was 85% dissociated. And for the last solution, it was 81% dissociated, right there. So it looks like there's a trend going on that the lower the concentration, the less dissociation there is. I speculate that's because I might have made a measurement error. There's a very high level of dissociation in all of the solutions. What we'll do with the acetic acid tomorrow are the same steps. We'll prepare the dilute solutions and measure their pH, calculate what percent of the acid dissociated, and then we'll plot it just like these values for the hydrochloric acid and compare them to see which acid is stronger, which one dissociates more.